Generations of expressive cartoon animation from captured mocap is a challenging task. It can also be noticed that squash and stretch is easier to realize in traditional animation than in computer-generated animation. In this paper, we describe a new and simple approach allowing animators to edit and reuse arbitrary animation with real-time control to produce exaggerated skeleton-based character animation. Our contributions rely on the skeletal graph Laplacian, differential joint coordinates, and cartoon optimization algorithm. We demonstrate that optimizing mocap skeletal bone hierarchy with stretching effects allows animators to efficiently reuse previously captured animation in the context of cartoon productions. Spatial occurrence of joints is preserved by differential aware scaling represented by a quadratic energy function leading to a Poisson skeletal solver. Please see the paper for more technical details. Our techniques has two key components: spatial temporal motion filtering and global joint locations optimization. First, our algorithm applies the cartoon animation filter in order to add follow-through exaggeration and anticipation effects on the motion simul. As far as no elasticity is possible in a Hurler space, we prefer to deal with the skeletal structure with Euclidean joint coordinates in order to hack the rigidity in real time. In our approach, we focus on adding non-rigid effects to an existing captured skeletal structure while preserving its consistency and the original connectivity. We are referring to the well-known Laplacian shrink-ring effects to apply non-rigid warping over the skeleton topology. We reformulate the squash and stretch problem as a skeletal adaptation optimization. Given the fact that it's nearly impossible to get a plausible squash and stretch by working exclusively in a Hurler space with inverse kinematics, we prefer to optimize the whole skeletal structure in terms of global joint location of a pre-animated pose satisfying stretching constraints. Contrary to previous work, we deal with the skeletal structure rather than its associated motion data itself. The core algorithm of our techniques rely on skeletal graph Laplacian with the aim to ensure spatial relationship of joints under sparse differential aware stretching features. The input solution is the Euclidean parameters of the animated pose generated by forward kinematics. Thus, pose estimation recovers the position by minimizing an objective function that is a combination of penalty and data terms. The resulting effects present the same appealing than traditional animation as seen in TV cartoons, but in 3D, and editing is not limited to human model or end effectors handles. Note that our techniques achieve coherent lower and upper body part with just a single drag and drop joint handle constraint applied on the opposite part. Smoothness is required for making the warp field regular. To control a cartoon desired pose, the user inputs the targeted global joint locations for a collection of edited joints. Real-life creatures actually elongate and stretch due to the elasticity of tendons. Consequently, breaking the rigidity of the underlying armature to produce cartoon rubber-like effects makes sense. The resulting animated structure looks more pleasant while remains rigid in motion. Screen space elongation bone constraints can be adapted automatically to lie along the bone direction. Global joint locations is estimated by minimizing the sum of square difference between the data-driven pre-animated pose and input feature cues, in order to avoid purely translational effects provoked by a single dragged and dropped joint. We fix by default the root joint, acting as skeleton gravity center. The root joint is generally located in place where many bones come together. Spatial coherence of joints is preserved by differential aware scaling integrated into the solving process. The usefulness and flexibility of our approach is fully demonstrated to design effective animated pose. In addition, we developed an interaction technique coupled with depth-first search to handle the closest joint. As shown on this video, just a single editing feature is enough for adapting the whole skeletal pose in current manner. To avoid a linear snapback, we enforce temporal smoothness by penalizing inter-keyframe deviation using iterative smoothing. Breaking physics of the motion rigidity allows us to obtain cartoon-like effects. How techniques can be used to achieve non-rigid animation, cartoon shape control, and elastic skin deformation from mocap data. Thanks for your attention.